Hello, good morning everyone, and thanks for being here. I'm Biswajit. I'm a postdoc at the City College of New York. I'm working with Professor Vinod Menon. Unfortunately, Professor couldn't be here because of his other commitments, so instead I'll be delivering this talk. So the title of the talk has changed a little bit, and today we are going to discuss about recent improvements that we have seen in strong coupling in our laboratory. In particular, I'll be talking about TMDCs and new van der Waals magnets. Now, we all love van der Waals materials. From a small crystals, we can literally make endless number of devices. Starting from graphene family, there have been a huge number of 2D materials discovered in literature, particularly 2D chalcogenides are the favorite of optics community because of many advantages. And recently, there are a few other materials, especially magnetic materials, that are discovered. And the cool thing is they also have exciton. Now, thanks to Arnab, he has already covered the basics of strong coupling. But a brief introduction. Throughout my talk, we'll be talking about systems that are strongly coupled to a microcavity. And what we do here is we basically sandwich a material hosting an exciton in between two mirrors, and under suitable condition, this exciton can get strongly coupled to the cavity. And such a system basically described by three terms. The first term is the cavity dispersion in a microcavity, which is a parabola. And then the exciton looks like a straight line in the momentum range we are interested. And the third term is the interaction between the cavity and the exciton. And when after strongly coupling, we have an upper polariton and a lower polariton, and there is a Rabi splitting between these two. Such a system, when illuminated with a light source, they typically emit photon from the lower polariton branch. Now, any system hosting an exciton can actually give you polaritons, but why TMDCs? What's special about them? In particular, TMDCs have very high binding energy, ranging from 0.1 to 0.3 eV, and that means the excitons can be observed at room temperature, and that gets inherited to the polariton as well, so it's easier to observe at elevated temperature. Along with that, TMDs have very nice value properties. One can excite a particular value over the other with a circularly polarized light. Again, the polaritons have these nice properties. A consequence of having large binding energy is that we can also observe higher Rydberg states, and that can also form polaritons. And recently, we have actually shown it. These large Rydberg states, due to higher Bohr radius, they lead to higher nonlinearity. They have a very large oscillator strength, which is very important to realize polariton in the first place. And people in the literature also explored trion polaritons along with exciton polaritons. And this part actually will be the focus of my first part of the talk, nonlinear property. Now, traditionally, people have observed nonlinear behavior at very high pump fluence. Now, in our lab, we want to go to the quantum regime. That means we want to shine the system with very few photons and still be able to observe high nonlinearity. Now, it has been a long journey starting from TMDC. In our lab, we first observed strong coupling in TMDC, and then a few years later, we observed valley polaritons, and in 2019, we reported polariton diode based on TMDCs, and very recently, we have reported Rydberg polaritons, and because of higher Bohr radius, they have very high nonlinearity. But today, I am going to focus on two different aspects. The first one is I'll be talking about something called dipolar exciton-polaritons. And in the second part, I'll be talking about spin-flavored exciton-polaritons in van der Waals magnets. So, so to start with, why in the first place we want a dipolar polaritons? Now, this is motivated by the fact that people want to realize this polariton blockade, and the idea is if you have a system where the polaritons are strongly interacting with each other, you can imagine this scenario when the system absorbs 2 photons and they get converted into polaritons. The polaritons interact with each other so much so that the energy level changes, and hence in such a condition the system cannot absorb another resonant photon. So, the system can absorb only 1 photon at a time. This is known as polariton blockade. And how can you realize that? You have to basically increase the nonlinearity in the system, and that's a basic motivation. And to realize that, in our lab we have taken 2 different routes, Rydberg excitons that I talked about, and very recently we have realized dipolar excitons based on homobilayer transition metal dichalcogenides, and people in the literature have also tried to use trion-polariton in that direction. So, dipolar polaritons actually have been realized in quantum Waals, and what they do is they make quantum Waals by MBE, which are separated by a thin insulating layer. And when you put a top and bottom gate across the structure, a little bit of electronic wave function leaks into the other layer, and hence you have a new kind of exciton across the quantum Waal. This is known as indirect indirect exciton. Now, this exciton has a permanent dipole moment, which is great because now the 2 excitons can talk to each other by dipole-dipole interaction. However, it comes at a cost. Typically, indirect excitons have very poor oscillator strength, and hence they cannot really absorb light efficiently and cannot form a polariton. The way people actually go around it is they provide bias so that they cross the direct exciton and the indirect exciton, and after they hybridize, the indirect exciton borrows some oscillator strength from the direct exciton, and after that they can further hybridize with the cavity and form polariton. But these sort of devices are usually harder to make. You require MBE to make this multiple quantum well, and then you need multiple gates around it. So, we are looking for something easier, and then we looked up in the literature. We saw homobilayer MOS2 and MOSE2, they support a particular exciton. It's called interlayer exciton, and the way it works is the charge distribution is peculiar. The electron is localized in one layer, but the hole is delocalized in both the layers. So, that leads to a permanent dipole moment perpendicular to the layer. But remember, homobilayer transition metal dichalcogenides have inversion symmetry. So, you cannot really break inversion symmetry at 0 electric field. So, you actually have another cousin of this exciton with the electron in the bottom layer, and at 0 electric field you have 50% of each kind. And when you apply an electric field perpendicular to the layer, people have shown that this exciton interlayer actually breaks into 2, and at higher electric field it further crosses with B and A exciton and further gains oscillator strength. But in our experiment, we will show that there is an even simpler route. You do not actually need to break the interlayer into 2. Even at 0 electric field, this interlayer exciton forms dipolar exciton-polariton and shows very high nonlinearity. So, what do? We take we exfoliate this hexagon. We exfoliate the bilayer MOS2, sandwich it in between 2 hexagonal boron nitrides, and cool it down at 7 Kelvin. We see a very strong absorption of interlayer exciton in between A and B intralayer exciton. It's the oscillator strength is almost 30% of A exciton. Then we do a power dependent blue shift experiment. What we see is as we increase the exciton density, the interlayer exciton shows much more blue shift compared to the A exciton, and that is again expected because the interlayer exciton is supposed to have permanent dipole moment, and that's why higher shift. Now, to study the nonlinearity of the interlayer polariton, we put this sandwich inside 2 mirrors. The bottom mirror here is DBR, dielectric Bragg reflector, and the top mirror is just deposited silver. And at low temperature, we see very nice, well-formed polariton branches. Here, in this sample, we actually see 5 polariton branches, and this is because there are 4 excitons here, A interlayer B, and it turns out at low temperature, the 2s Rydberg state of A is also strong enough that it couples to the same cavity. But the focus here is to study the nonlinear effect, and hence we choose these 2 particular branch, the second and third branch, which have the maximum interlayer exciton character. And what we do is we increase the power of the laser which tunes the polariton density and study how the energy changes of these 2 polariton branches. We see the exciton blue shifts, and at the same time the Rabi splitting starts quenching. And from the lower polariton energy shift, we can calculate the strength of the nonlinearity. It's called G factor. And from the curve, you see the green curve is for interlayer, and the red one is for typical intralayer A exciton polariton. At low polariton density, which is where we are interested, we see a factor of 10 improvement of nonlinearity. And this is a very good news because that's what we wanted to see, and the dipole-dipole interaction is playing a role to improve this interaction. Now, the question is, are we in the polariton blockade regime? We are still not, and we can calculate how many photons do you need per micrometer square to shift the line width of this polariton by one line width. And the answer is roughly we need 100 polaritons currently per micrometer square to shift the energy by 1 line width. It's not yet in single digit, but we can make further improvements. We go on and further find out what are the mechanisms behind this improvement. Turns out there are 2 different mechanisms here. One is phase space filling, and another is exciton-exciton interaction. And here I plot the ratio of these 2, and you see at low polariton density, the exciton-exciton interaction is increasing, and that is highly desirable, because even though both the mechanisms lead to higher nonlinearity, saturation mechanism actually quenches the polariton itself. So exciton-exciton nonlinearity is preferred. So you are going in the right direction. That brings me to the summary of the first part. What we have shown is that using bilayer MOS to interlayer exciton-polariton, we see a huge improve in nonlinearity, and we also recall that so far we do not have bias in our experiment. So we think when the system is biased, the nonlinearity will improve even more. So now I'll change gear a little bit and go to the second part of my talk, which is on realizing spin-flavored exciton-polaritons based on van der Waals magnets. Now here, there are 2 major players in this. The first one is nickel phosphorus trisulfide, NiPs3, and the second one is chromium sulfur bromide, CrSbr. They are similar in some ways, but they are dissimilar in many other ways as well. So in the first part, I'll cover NiPs3, and in the later part, I'll go into CrSbr. Now, NiPs3 is a correlated insulator with a gap of 1.7 electron volt. So it emits roughly in the near infrared. It's also an antiferromagnet below nil temperature of 155 Kelvin. And it is also air stable unlike chromium iodide. But the most important thing is, along with being magnetic, it also hosts 3 kinds of excitons. Interestingly, the emission from this NiPs3 is very highly linearly polarized. Turns out, even in late 90s, people studied magnons in NIPS3. And more recently, Rick's experiments show the polariton, the magnon branches in this material. And people have also been able to excite magnons and probe them with a laser above the band gap. Now, what are the questions that we are trying to ask here? So it's very interesting. It appears that the excitons and magnons in these systems are coupled. So we ask, what are the origins of these excitons? And what's the role of the magnons? And are they coupled? And if they are coupled, why is it so? So to answer a few questions, we first do some experiments on regular exciton. And the first thing we see, this was already reported in literature, the line width of the excitons are very, very narrow. It's almost reaching 500 micro eV. And the emission is highly linearly polarized, around 83%. And if you do absorption experiment, you see 3 peaks, 3 absorption. And it turns out DFT calculations show that these excitons are actually formed in between nickel d orbitals and sulfur p orbitals. Now, nickel d orbitals, as we all know, they have long range magnetic order. So these excitons are inbuilt related to the magnetic order in the system. And people have also shown that once you rotate the magnetic field, the polarization also rotates. Now, to study this new kind of exciton-polaritons in NIPS3, we take a bulk flake of 170 nanometer thick and put it inside a cavity, and we see all these 3 excitons actually get coupled. And this is a DBR silver cavity with a modest line width, and the excitons are very, very narrow. And that's why you see a very disparity in the line width. And as expected, as we increase temperature, the polaritons go away as you go close to the nil temperature. We also study the polariton emission from this sort of polaritons. What you typically observe in other materials is the polaritons actually scatter to the bottom of the lowest polariton branch, but here something unusual happens. We see that most of the polariton emission is coming from close to the exciton location. So that's kind of weird, and why is it so? And we notice that this scenario changes a little bit when you do the experiment at higher temperature. And the way we understand this is the excitons in this system are highly localized, and hence any exciton-exciton interaction is suppressed. So the way the exciton come to the bottom of the branch is by exciton-exciton interaction or by phonon. Increasing the temperature, the phonon from the temperature helps for the polariton to scatter to the bottom of the branch. We also study the polarization. We see the polarization, the degree of polarization is now reduced for the polariton case. It's roughly 50%, and that's understood because of TETM splitting. Now, the nonlinear interaction also shines some more insight about this kind of excitons in NIPS3. So here what we do is we resonantly pump all the exciton polaritons and observe their energies as a function of density. There is no blue shift in our experiment, but for the lower 2 polaritons, the Rabi splitting slightly decreases as a function of density, but that happens at very high density. So from fitting these curves, we find the saturation density, and from the saturation density, we can calculate the Bohr radius, and the Bohr radius turns out to be around 6 angstrom. And again, this only proves that the excitons in these materials are highly localized, and are pretty small. That is why the excitons don't really talk to each other. They're kind of independent. So what we have shown is the excitons are very localized here, and the excitons are intrinsically coupled to the magnetic order, and you can, even though we haven't shown here, we show in the other case SPIE that magnetic field can be used to rotate the polarization. Now I come to the last part where we study the other cousin of this material, SPIE. They are actually different in many ways. This is also an antiferromagnet, but along with that, the crystal structure is very anisotropic. This can be thought as 1D chains which are talking to each other weakly. And this we can see even in experiment. If you take this material and try to exfoliate it, this will easily cleave along a very narrow strip. The band gap is slightly lower, 1.5 eV, and the Néel temperature is slightly lower as well, 132 Kelvin. And the good thing is this material is also air stable. The reflection and the PL measurements show the existence of a bunch of excitons which are still people don't understand their origin completely, because there seems to be more than one excitons. And another interesting thing about this material is this material has a very high refractive index. So for this, we actually often don't need any cavity spacer. We just take the material and put it on a DVR and deposit the top mirror. And depending on the thickness of the material, we see different number of polariton branches. For this thickness, we observed 2 polariton branches. These are all lower polariton because this is a photoluminescence measurement. The upper polaritons don't show up here. Since these polaritons are magnetically coupled, we should be able to see the effect of magnetic field. So what happens when we apply a magnetic field either parallel to the layer or perpendicular to the layer is that the spin starts rotating, and at the saturation magnetic field, all the spins are aligned and it becomes a ferromagnet. It has been shown by DFT that when the system is for example, in bilayer SPIE, when the system is an antiferromagnet, the wave function is localized in one of the layer. But when it becomes a ferromagnet, the wave function is delocalized in both the layers, and that has a consequence in the exciton and polariton energy as well. So here we plot the energy of these 2 polariton branches that I showed before as a function of magnetic field. At 0 magnetic field, you see the energy is the highest, and when the material becomes ferromagnet, the energy decreases. And for this sample, the energy decreases by 15 MeV, but it's a function of the cavity fraction and exciton fraction, and can change from polariton branches to polariton branch. We can also excite magnons, and we find that the polariton and magnons are coupled in this system, and for that for this experiment we collaborate with Professor Xiaodongshu's group, and what they do is we plot the transient reflection, and the probe here is broad enough that it covers both the polaritons, both the lower polaritons, and we plot the transient reflection as a function of magnetic field and the pump probe delay. So the pump excites the magnons, and the magnons and the excitons are correlated, and that's why you see the oscillations in the transient reflection as well. As a function of field, since the magnon frequency changes, so does the transient reflection of the exciton. Now, if you take a Fourier transform of this 2D data, we see the magnon frequency which is dispersive as a function of magnetic field. Now, here there is a small splitting between these two, and this is because the magnons are also coupled to phonons, and that leads to a very small splitting here. Now, another interesting thing about having a thick flake is a thicker flake sustains many, many polariton branches. In this sample, we see around 5 polariton branches here, and for every polariton branch, the exciton fraction and the cavity fraction changes. Now, earlier I showed you that the magnetic field actually can tune the energy of the polaritons, and more precisely, it relates to the exciton fraction. Now, in this sample, the exciton is here, and the further you go from the exciton fraction reduces, and hence the magnetic shift should reduce as a function of detuning. And that is what we observe here. Here we plot the magnetic shift as a function of polariton detuning for all these branches, and we see that the magnetic shift is monotonically reducing as a function of increasing polariton detuning, and it is a linear function. This is a cool way to modify the polariton energy and differently for different branches. So, with that, I would like to summarize my talk. What we have shown here is magnetic field can be used to change the polariton energy, to change the polariton wave function, and the magnons and the polaritons are all related in this material, and the magnons can be even excited with a pump laser just above the band gap. And with that, I will like to thank all my collaborators, Professor Stephen, Simone, Eduardo, Professor Alan McDonald, Professor Andrea Liu, Professor Sofar Xiaodong Xu, Akasdeep, and Francisco. And with that, I thank you for your attention and welcome any question you have.